one safety issue again, and it's in addition to nano, the problems of nano, I'm going to add radio here. So nobody does not like nobody does like the radio or nuclear, because our kind of a collective the memory of nuclear bomb or the nuclear threat. But since 5 decades ago, the radio or nuclear technology or the radio stops has been used for health promotion and also disease the treatment. So as a nuclear medicine physician, I'm quite familiar with the nuclear technology and also the radiation. And also, as I told you, the radiation oncology has become an independent discipline to help people definitively. So we call it the combined radiochemotherapy, CCRT. So, today's talk is the radionanomedicine, and I'm going to tell you about what radionanomedicine is, and what are the promises, and what are the problems, and how to overcome those problems. And it was supposed to include the exogenous and endogenous. However, as I told you, because of the reason that I told you yesterday, my talk has been split with my dear colleague, Professor Huang. He's going to tell about the endogenous part tomorrow. So I'm going to pay my main attention to the exogenous ones. So the nanomaterials might consist of exogenous, might be classified as this exogenous endogenous one. And exogenous one, it can be also classified to the inorganic and organic. And organic material, you have heard the legacy as the legacy, the stories about liposomes. And tomorrow, in future prospects, we are going to listen to the extracellular vesicles here, like this, and nanocosmos and imaging strategy. So, what is radionanomedicine? And there are subfields of nanomedicine, molecular imaging using nanomaterials, or the targeted delivery and therapy using nanomaterials. If we put the radioisotope upon the surface of the nanostructures here, such as the gallium, copper, and zirconium, and for a treatment and lutetium, and we have these numbers, which is saying the weight of the molecule and a combination of the neutron and proton. And then we are having the radio nanodrugs, or radionanomedicine, or radio nanotracers. So then I'm going to talk about this radionanomedicine. Before entering into the explaining, then explaining I'm going to just summarize very briefly what we know and what you do not know. That's molecular radiotherapy. We call it molecular radiotherapy. Versus external beam radiotherapy, which is done by the radiation oncologist. We have now the bone targeting radium chloride. Radium is just a radium, very famous chloride, which has a kind of a range of just 100 micrometer, and name is Xofigo, which is widely used to treat the metastatic bone disease. And we have transarterial yttrium-90 microsphere. It should be embolized to the hepatocellular carcinoma. It's called radioembolization. And we have the commercial product here. And the size of the microsphere is 30 to 50 micron, which will block an arteriole and SIR spheres, therasphere, consisting of the glass or resin. And we have another another tool of the treatment strategy, peptide receptor radionuclide therapy, named by Professor Richard Baum of Bad Berka, previously Frankfurt University of Frankfurt, and he called it PRRT. Everybody is saying the PRRT. For this, receptor is targeted and peptide is used, and the radionuclide is labeled with a chelator. So they use the yttrium-90 or lutetium-177. And here we call it DOTA-TOP, and TOP is the name of the peptide. And the kind of analog of somatostatin or octreotide, whatever. And DOTA is chelator. DOTA is, the DTPA is a famous chelator. And DTPA and DOTA are the same group. And these radioisotopes are beta emitters, and 2.3 mega electron volt is beta max. Its range, because the electrons have the very high energy. It has a kind of a penetration, but according to the energy, they can penetrate up to 10 millimeter in tissue or 1 millimeter. But they have, as a radioisotope, another characteristics of half-life or the decay constant. And half-life is easy to remember, so we use the yttrium has a half-life of 3 days, and lutetium has a half-life of 7 days. So you can just memorize that the higher energy, deeper penetration has a short half-life, and the lower energy and because of the lower energy and shallow penetration, but have a longer half-life. So the problem is to treat the neuroendocrine tumor of Steve Jobs. What kind of the isotope should we choose? Actually, Basel University Hospital chose, as I remember, lutetium, and there has been a kind of an alternative yttrium. So let me just because this is a tutorial session, I just refer a textbook which I learned 30 years ago. So as a kind of a morning refreshment, I have prepared 2 slides. Please excuse me to let you see the equations. That's survival fraction, and tumors should not survive. The survival fraction is 0 to 1. 0 means all tumors are killed. 1 means no tumors are killed. And here, a long while ago, the log, natural log of survival fraction here, natural log here, survival fraction is 0, and the log is minus infinite, and the minus log is just plus infinite, and 1 is 0. And they found that experimentally, the survival fractions log is not linearly proportional to the dose of the radiation. It's just curved. Why? We have the second term. Actually, third term and fourth term and infinite polynomial term can be used, but they have just so this is kind of a radiation real effect. So because we are using the kind of various protocols or various radioisotopes, so they have devised a biologically effective dose BED, and by just putting alpha out, and this is the same. So BED and BED. So next slide is depicting. So, but in case of the external beam radiotherapy, they just put radiation to the tumor tissue, and the normal tissues and tumor tissues are responding differentially. So BED for external beam radiotherapy using the same equation, after a while, they have started to fractionate so that the normal tissues can recover differentially while the tumor tissues are dying. So after fractionation, they found that the beta, the second term is just determining the curvature of the curve, and the curvature is like this, and then more tumors are killed, or the more normal tissues are damaged. So once they have been fractionated, so beta is divided by n. So what about the radioisotope? We do the radioisotope, radiopharmaceutical, we inject the people, and then the radioisotopes are staying there with the physical decay and also biological excretion. And combining both, we call it the effective half-life or effective decay constant here. And they found that recently, and it was summarized by these Italian colleagues very well in the Frontiers of Oncology, very easy to understand, and beta can be modified by this one, just like n. And why? Let me explain. And then lambda effect is just effective constant, but it is modified by the repair constant of the tumor tissues. And repair constant is known to be 0.53 here, and the effective decay constant is in this range. Why? Because, as I told you, yttrium has a 3-day half-life and lutetium has a 7-day half-life. So this is the reality. If mu repair is higher than, and then it is this is gone, and this is like this. And let me just calculate. If T half is 3 days and lambda effective is 0.01 per hour, then beta is divided by 54. So we are just doing the same, but situation is different. Yeah, the molecular, the radiotherapeutic drugs are already in the body, and it is decaying or it is excreted. So that's the story, and that's the quite a good, very brief summary of the molecular radiotherapy and their effect. So if I summarize the problems of radionuclide therapy, theranostics, we need to predict. After that kind of calculation, we need to do the clinical the application and predicting the therapeutic effect of the lutetium and yttrium labeled ones with the imaging. So they have done. Dotatok was labeled with another imaging radioisotope, and they found that its normal organs, the ratio, the linearity was well maintained. However, the tumor dose is a little bit different. And also, we need to protect the kidneys or other organs, critical organs, while just the killing tumors, we don't want to kill tumor. And this is Johns Hopkins compound, which was published several years ago, Journal of Medicinal Chemistry, and they were satisfied with this imaging compound. And here, PSMA positive prostate-specific membrane antigen, which is also folate hydrolase 1. They are visualizing this well, but kidney is better, and 10 times higher, 10 times better visualized. For imaging, it's okay. Why? Because prostate cancer does not metastasize to kidneys. However, in case of the therapy, while trying to kill the tumors, you're just injuring, damaging the kidneys. So how to combine those lutetium and yttrium? So why don't we just use the nanoparticle platform to combine this? So nanomaterials labeled with radionuclide to solve these problems, and that's a starting point. So if I just list several nanomaterials here, increasing sensitivity and increase the hybrid imaging here, and then PET, and also MRI, or the conversion nanoparticle with SPECT in iodine 125, or surface interferon scattering dots to enhance the Raman signal, spectroscopic multiplex capable signal to the extreme, and we cannot detect the surface dot, so we just label the fluorescence probe over the surface, and all those I'm interested in the everything. However, during this talk, I'll talk about the only in vivo PET MRI, or the in vivo topical. I'm not saying in vivo. So for in vivo, the administration and intravenous administration, we have several concerns here. The safety concerns might be related with the. I just told you about the radiation hazard, and nanomaterials have its own concerns. The carrier-related, nanomaterials related, and also the surface ones. And pegylation, is it the solution? No. We heard yesterday the PEG-related ones, and this evening we will listen to the PEG-related ones again, and also surface, and also cargo. Here, adriamycin, doxorubicin can be should be toxic to the tumors, but it might be toxic to the normal organs. So that's the reason why the Doxil has prospered. And photoactive drugs here, the photothermal therapy, or here. And yesterday, Professor Chen told you just a little bit, saving a little bit of time, PDT and PTT. And also, I'm just telling you about the radionuclide. For in vivo nanomedicine, and we need to learn by this region to learn whether the injected radio-labeled nanomaterials are going to affect the tumors or the target organs or the normal. So please refer to Joan's talk of yesterday. They do persist permanently, or they are excreted. We need to understand that. And the safety and toxicity issues, and sometimes contents related cadmium will not be allowed. Or the shape. Carbon nanotube is well known for their kind of a toxicity, just like a silica. We know as a physician, we know very well silicosis is detrimental, and carbon nanotube is like that. So I don't think the carbon nanotube. Then what about the instead of the carbon nanotube, the graphene? So that's the question. And surface reactivity, positive reactivity, and positive charge, and hydrophobicity should be prevented. And so the summarize as a kind of a radionuclides. There are so many radionuclides, and Wikipedia, you can just browse everything, but this is a summary. Commonly used but bad, in my opinion. Iodine 131, and gamma and beta emitter. Beta emitter is quite cumbersome. And their half-life is. Indium is gamma. However, the T-half is long, so you need to use the 1/10 of the technetium. So image is blurred. You have less photon flux. You cannot make a good image. Gold 98, a beta emitter, pure beta, so you cannot make any. Well, you can use the Bremsstrahlung, but it is not. So this is recommended. Copper 64 and positron emitter. You need a positron PET and PET. And T-half is 13 hours. Line of response is making a good image. And technetium 99 MR, and we have these days in microspec CT, very good. And yttrium 90, sorry. And lutetium 177 and rhenium 188. That's a beta emitter. Sometimes they emit and gamma. So gamma image can make an image. Less recommended here, gallium. Gallium is quite widely used, but its half-life is short. So if you are going to use to track until the next day and several days after, the gallium is not appropriate. And zirconium is appropriate, but zirconium chemistry is very difficult. So far, my very good friend, the very eminent radiochemist, he could not succeed with our cyclotron. So these are the images you might just enjoy. This is image here. That's technetium microspectroscopy, and this is copper 64 PET CT. So you find a misalignment. Why? Because we use the only we image the CT once and then the PET several times. So that's the story. Then move on to the next one. I have 20 minutes. The middle 10 minutes are going to be devoted to the promises of the radionanomedicine. This is a summary. You can just memorize this. Advantage of radionanomedicine. Radio means we can just decrease the amount of the injected material down to 1 million, or the pharmacological amount, in theory. And trace amount, we call it trace amount. And also, it is emitting radioactivity, so we can do the image, PET inspect, and tracer kinetic. It's different from the MRI. MRI should give almost 1,000-fold of the concentration. So that's the reason why they experience use because of the gadolinium, the nephrogenic systemic sclerosis. And also sometimes it might be both imaging and be used both imaging and therapy. And the professor allowed us to summarize all those findings in this review article last year. So trace amount, please be reminded that there is no pharmacological effect, but we need to worry about the radiation effect. And why I am interested in the nanoparticles is because of their vast surface, which can be modified. This kind of 20 nanometer diameter is giving us the 1,000 square nanometer for all those microRNA or antibody or pegylation, whatever. And in a recent report by this group, HS Nano, actually several months ago, they contemplated and just to summarize the individual nanomedicine here. If individual nanomedicine is given in combination, then we just hope stochastically, probabilistically, distribute to the tumor at the same time. But those tumors, sometimes the heterogeneous stem cells, or sometimes in different sites, they do develop resistance. So they devised a 2-in-1 nanomedicine in the same nano. Here, deterministic drug distribution, and that's the concept presentation, and the real details are complicated. So multiplexing is this kind of. Which nanoparticles? Gold nanoparticle is just like this. Antibodies. Antibodies is actually nano. 11, 15 nano. And albumin was proposed nano yesterday by Professor Kun. And iron oxide nanoparticle was smaller than. And this is peptide and salicylic acid. Andy White has depicted drew these pictures and he put in his book. And the nanoparticle does not have any inclination, any proneness to come to the target tissues. They need to be guided by small molecules and macromolecules, and having the surface. So let me talk about the small molecule. We are using this one 50 cases per day for PET here, and 10 cases per day PET MRI. PET means PET CT, and this is MRI overlaid with the PET, and you can find the glucose metabolically high tumor tissues. And if you they change the is it racemol? No, enantiomer. And hydroxyl here, this is galactose, and hydroxyl is not here, and mannose, and galactose is targeting hepatocyte, and mannose is targeting copper cells and macrophages and nanomaterials. So it is natural. It's obvious that we have still the debate of the passive or the active targeting as a mechanism of action of nanomaterial targeting. Still, it is not resolved, and I'm very curious about. So those macromolecules based on combinatorics and antibody and almost infinite combination and aptide to by John from KAIST. And nanobody here and here from KEMR. There's an expert in this institution, in this college, KEMR antibody, but KEMR has a horrible fame last year because of the MERS. And non-natural peptide from Tokyo University, he has made a non-natural peptide, and to teach it, amino acid transfer the transferase, and let them know, and they and all natural peptides or so, and also I just propose to the young, the next generation. When you think about the here ligands, targets might be considered as antigen, and immunoglobulin is so dominant. And however, our body is using TCR, less affine but more rapid. So TCR to antigen, they are just the recognizing not just the antigen, and they do recognize the major histocompatibility complex molecules. So those antigens are presented in either way here. So recently they have even chimeric antigen receptor, and our immunologist has done a great job to do this one, T cells. Or why don't we use the kind of less affine and more rapid the ligands upon the surface of nanoparticle? Why? Because we have a huge surface. That's mine. So let me talk about the surface modification. The surface modification has two issues. One is the multiplexing. At least PEG and then ligand and chelator. Here they have done simultaneous chemical labeling and this group and this one and this one, and yield has dropped much, but they have succeeded in making this. But my colleague has adapted actually as they developed this here, lutetium and gallium at the same time, and this is called physical labeling for this kind of combination or this kind of combination, combined internal radiotherapy or prediction. And conventionally, if you are going to pegylate and target ligand labeling and then radioisotope labeling, one step, labeling and purification, labeling and purification, labeling and purification is going to decrease the yield unpragmatically, unrealistically. But the difficult QC and the RI labeling of radioisotopes are also causing a problem. So my colleague's method is just kind of making a good micelle and then combine it. That's it, the one step. So we can just deal with the combination of zeta potential and size. In terms of the toxicity studies, we can use the same strategy here. Dr. McNeil has summarized it very good. So he is my colleague. He just used the twin and functionalized amplifier micelle and the hydrophobic quantum dots and mixing and vortexing and filtration. So he just proved in vitro the specificity and selectivity, and that was the combination. Peptide and chelate, and sugar and chelate. And lactose or targeting is expected to hepatocyte and mannose or corpus cells. And this RGD was targeting the tumors. And so we have used the same materials here for encapsulation. We called it encapsulation. And this kind of a hexagonal UCNP, as you heard yesterday, and pegylated and at the same time, and chelator and pegylator and radio labeling, just to one step and radionuclide second step, like this here. And we use the Van der Waals force, and these are all PEG materials. And we use the 60, the carbon type. So we found, interestingly, it is excreted via gallbladder to the intestine, not just taken up by the liver. So please don't assume a priori the liver uptake is going to be by copper cells. No, liver has many cells, and hepatocyte is major. Copper cells are the minor. Here, gallbladder means it is dealt with. And also, UCMP has proved it. Luminescence emission, and core and the capsules were detected at the same time simultaneously, and even fishes, luminescence emission and PET. So we could just say that kidneys were saved. Yeah. We are going to use the PSMA ligand to modify the surface, and it is automatically imagined that the kidneys are saved and it's excreted here. Only 10 to 20% are remaining after 72 hours. So that's kind of a biological excretion. So that's against the data you've heard from Professor Johansson. And so that's the reason why I asked him. His gold experiment using ICP-MS is gold standard. But what about the silica or the other UCMP type of molecules? We have seen here, kidneys were saved. During that time, the Wolfgang Fark, the associate editor of the ISNM, they published this. And I heard about this work from him during council meeting last year. He just did this kind of amide bond here and labeled the capsules with indium and cores with gold. And he wondered, those are excreted like this or like this. And finally, he found that gold is not in the feces or blood, but the indium is feces. So this definitely shows that the capsule is detached. So some of the encapsulated the nanoparticles behave like this and behave like this, like this. Okay. So we need to understand. So in vivo stability, what determines? So there is a difference. We've used the thiourea here. They have used amide. That's the only difference. We can just speculate. The second one is the preservation of functional activity of ligands. The ligands itself is good as themselves on their own. However, what about if we put on the surface of the nanoparticle? Is it okay? Sometimes the antibody hypervariable portion is just upside down. Then we have only Fc receptor. We don't want Fc receptor nanoparticle. So he devised, he adopted a click reaction here, azidenarachine and azide here, click over 1 and adipo DDCO at the time. And multiplexing was already again possible and combined them. And multiplexed clicking. And also, we did a RI pre-labeled chelator, and that's kind of a compounding. So we want to overcome the manufacturing issue and regulation issues. So radioisotope is the only exemption from manufacturing because of their short half-life. So every day we do just a kind of a chemistry on site. So nanoparticle is prepared well, and then this kind of pre-label chelator, we have 2 bottles and just mix and then inject. So the FDA guys cannot regulate that compounding. They just request CGMP. They just kind of the documentation. And it costs a lot, but we can do that. And also, it could be used that click reaction to let the antibody upside up, not upside down, on the surface, and it was working. This paper is under revision. And then, secondly, we can just use the tracer kinetic here. This time radioactivity curve can be used as an input for this kind of the compartment model. That's what is compartment model, and let me tell you. EPR, they have found EPR is going to attract a nanoparticle, and ligand, in this case a transferrin, is adding the retention. So we can just dissect the initial K1 and also retention, the decreased K3, that kind of. So this is the model, which is in the textbook of the nuclear medicine. And as an MD, I know very well the Kitai-Schmidt and Rankin-Krohn model, and this is using compartment, and this is using the tube model and permeable tube model, and whatever. And the 2 great big shot here, Dr. Patlak and Dr. Rowan, he and she has made this kind of successful linearization. And they could just easily find the radioactivity input, then find the parameters to explain the kind of they're gathering together and staying there. It's called enhanced permeability. And so permeability means immediately this one, but we prefer to use the compartment model. So based on this kind of idea, volume of distribution means that the concentration is lower. And if the concentration is same, then volume is shrunk. So that kind of, and which was used successfully by other group, IEEE Transactional Nanobioscience. That kind of journal is there, and they have used this one, and maybe they used this one. So design radio nanoparticle from the standpoint of accretions and trace amount used, evading RES and sparing kidneys and being excreted via liver and intestine, targeting the targets and evading innate immunity. I don't know anything about the innate immunity, so they should be done experimentally. So we are using this one. So that's to understand the bodily response. My colleague, who is now in Wisconsin, he had done with Professor Kai. He had done just to re-inject the nanoparticles. He used at the time the graphene labeled with something, and at second injection, the clearance pattern was, which is well known, accelerated clearance, ABC, blood clearance phenomenon, which is mediated by IgM. They have found IgM. So, because I'm interested in, I just try to search, is it the problem of the PEG or the PEG modification? Or what about if you change the, instead of the ethylene glycol, what about the N-methylglycine, polysacchars? Somebody is saying that polysacchars is better than PEG. Somebody is saying that no, it's the same, and sheet and globular ones. And somebody is saying the hyaluronic acid is added and it's okay. So we don't know right now. And you need to understand that. This is my last slide. And strain is affecting. When you are using bulk C mouse and DBA mouse and C57 mouse, the clearance is different. Strain is affecting, and which is which has appeared in Journal of Clinical Investigation, which has a very high eigenfactor value and which is a trustworthy journal. And the biodistribution depends on genetic constitution or immunity variation. Genetic constitution is just a general bodily constitution, and immunity variation is okay. So this is my slide using radionanomedicine. So even though we have added one more problem of radiation, but it might just solve several of the nanomaterial. Why? Because nuclear medicine physicians are so that, I mean, they are so versatile for the last 40, 50 years to use radiation source, not just outside as a X-ray generator, but just being injected to the humans, even to mine. So the expected by. Thank you.